Hi, welcome to this lesson on calculus, the second derivative. Let's have a look at question 1. So we're given a function f of x is negative x plus 2 all squared plus 3. We want to classify any stationary points, the intervals where the function increases or decreases, and then we want to classify intervals of concavity and if there is an inflection point. Okay, so first things first, what kind of function is this? So I can see if I write out f of x, this is in the completed square form, or otherwise known as the vertex form, of a quadratic function, a parabola. So the turning point given by PQ, in this case, is equal to, so what makes the inside bracket 0? It's x equals negative 2, and then the Q value is positive 3. Okay, so let's get a rough sketch of this diagram going on. Got my y-axis, got my x-axis. And before I do that, what I want to just check is what the y-intercept is. Okay? Because I already know that at negative 2 and positive 3, that's going to be my turning points. A maximum turning point, mind you, because a is negative 1 here, which is less than 0. So it's got that sad face shape with a maximum turning point. Okay? But also, I want to know where does it cut the y-intercept. So when I put x equals 0 for the y-intercept, I get f of 0 equals negative 0 plus 2 is just 2 squared plus 3. But that's going to be 2 squared is 4 times negative 1. It's negative 4 plus 3. So I get negative 1. So the reason why I'm doing that, 0 and negative 1, is that I can know then that the graph will have this kind of shape. It'll go up here, turn, come down, and then go through the y-intercept. Okay, so it looks like both x-intercepts are on the negative side of the x-axis, which we can work out if we needed to. But for our purposes, this is good enough for the function f, because now we can start exploiting the properties of the first and second derivative. So what I'm going to do firstly is I'm going to expand that function out so I can see the full thing. Then I can do some calculus on it. So if I square out the brackets, I get x squared plus 4x plus 4. Okay, so that's squaring out this term. And then plus 3, and then don't forget to distribute the negative into the brackets. So it's negative x squared minus 4x. Then you're going to have negative 4 plus 3, which will give you negative 1. So there's that y-intercept. We've got it in the form ax squared plus bx plus c. So our y-intercept is definitely correct. Okay, so now for stationary points, I need to set my first derivative equals to 0. So I use my power rule and sum and difference laws for derivatives. And I'll get that the first derivative is equal to negative 2x minus 4. Set that equals to 0 and then solve. So I'll bring the 2x across. I get 2x equals negative 4. Then divide both sides by 2 and I get x equals negative 2. And again, that's not a surprise. At negative 2, we expect that to be the stationary point for a quadratic function because it's the turning point there. So the derivative at that point is equal to 0 for that tangent line. Okay. What about intervals of increasing and decreasing? Well, if we just look at the graph visually, we can actually see that the graph is increasing over here, and then suddenly it turns and then it decreases over here. Okay, and more so because we can start to put these pictures in our heads and start interpreting them very nicely when we can towards the derivatives. Look at all the tangent lines I drew. They all lie above the graph, so the graph is down from the tangent lines. So dare I say it that this graph might be concave down on the entire interval that it's defined on. But again, that is our visual cue in terms of the graph, but let's also show it algebraically through differential calculus and confirm that theory. So where is it increasing? That's the first derivative greater than 0. Okay, so that's solving this linear inequality. Negative 2x minus 4 is greater than 0. So again, what I'll do is I'll bring the 2x across. So I have negative 4 is greater than 2x. But the way I would read that is 2x is less than negative 4. Okay, so I like to have my x's on the left-hand side. So this is equivalent to saying negative 4 greater than 2x is just saying 2x is less than negative 4. Then I divide both sides by positive 2, which does not change the inequality, and I get x is less than negative 2, where x is a real number. So I prefer interval notation. That's x is an element from negative infinity to negative 2, and that is the interval where it decreases, and we can actually, or increases rather, and we can see that's true. Look at all these blue tangent lines, they have positive gradients. Okay. decreasing, again, we're solving that exact same linear inequality, but less than 0 this time. So we have negative 2x minus 4 is less than 0. So what I'll do is I'll take over the negative 2x. So I'll have negative 4 is less than positive 2x. But the way of reading that is just saying that 2x is greater than negative 4. Then I'll divide both sides by 2, which doesn't change the inequality. So I get x is greater than negative 2. Okay, that's the inequality notation, but I much prefer the interval notation. So that's x is an element from negative 2 to positive infinity. And again, we can see the gradient lines are negative, so it's decreasing for that graph, and it lies above the graph. So the graph is below the tangent lines. Okay, so lastly, let's do the second derivative test, and that'll tell us the concavity intervals and if there's an inflection point. Well, the second derivative now is the derivative of the first derivative. So the first derivative we worked out was negative 2x minus 4. Now we take the derivative of that. And using our derivative laws, we get negative 2 here. So it's just negative 2. That is the entire second derivative. It's always negative 2 for all the real numbers x. So what does this mean? This means that our second derivative is always less than 0. But what does less than 0 mean in context? Well, that is telling us concave down. So our graph is concave down for all x values. So it doesn't change concavity anywhere. It always remains concave down. And we can see that visually. It's got the concave down shape. And also all the tangent lines are above it. So the graph lies downwards from the tangent lines. It's below it. Okay, so this mathematically makes sense both algebraically using calculus and visually from the sketch of the function. Okay, so because it's always negative, it can never equal 0, therefore it doesn't have any inflection points, and the concavity is that it's always concave down for all real numbers x. Alright, I'll see you in the next one.